Everyone. This is Tariq Khalifa, graduate research assistant from Texas A&M University, and Dr. Chin, also from Geophysical Insights, Mr. Alvaro, senior geophysical advisor. Today, we will deliver a presentation about accuracy assessment of the new Paradise Lithofacies workflow at the Illinois Basin Decatur CCS project in the US. In the beginning, let's us talk about our outlines. First, we'll introduce the area of study and the data set. Also, we'll talk about our motivation and the workflow, which consists from three different parts: selection, the seismic attributes, also the lithofacies prediction and the validation process. Also, part three, we'll talk about the lithofacies prediction results against seismic inversion results. Also, as the final part, we'll talk about the CCS application by which we will implement the results from lithofacies prediction, and we'll see how effectively these results can be implemented in carbon storage. So, talking about the Decatur project area of study, it's a large-scale project, and the injected volume it's 1 million ton, and the injection period extended through 3 years, starting from 2012. Currently, the monitoring activity it's all ended, and they started a long-term monitoring activity after 2020. Also, this project is unique because it represents integrated carbon capture and storage system, starting from the source to the subsurface reservoir. Here is our data set. We have three wells for prediction, and also one well for validation, which is CCS2. And here is the interval of interest, which is the lower part of Mount Simon, lower part and the middle part. After that, we will try to clarify why we need this lithofacial prediction workflow, specifically for this interval of study, because it represents a mixed lithofacial. So it will be hard using the conventional and the traditional workflow to separate between the subtle variation or transition zone or the mixed facies like medium fine sand and the shaly sand and so on. So, talking about our motivation and workflow, the challenge here, as we mentioned in the previous slide, it's a complex and interbedded lithofacies and a complex setting. So it will be difficult to distinguish between the different lithofacies using the traditional workflow. So here is our motivation, is to distinguish between them, and the most important one is to resolve the transition zone, which affects the injection process and the effectiveness of storage of carbon dioxide. After that, as expected, we needed advanced workflow like Paradise Lithofacies prediction, which we will implement, and we will explain the result that we get from it through the presentation. Here is a detailed workflow, but we will not go dive in details into it. We'll just highlight the three main parts of the workflow. The first one highlighting the seismic attribute selection. The second one highlighting the lithofacies prediction workflow and the validation process. And the third part talking about the comparison between lithofacies prediction against the seismic inversion. So starting from workflow part one, talking about seismic attribute calculation and selection. Here is we have the original seismic volume, and after that, as expected, we have a wide range of seismic attributes, usually more than 100 or 50 attributes. We just focused into three categories of seismic attributes based on our interest and our expected results. We focused on instantaneous attributes, texture attributes, and spectral decomposition. So the next step, we implemented the PCA, Principal Component Analysis, in Paradise. We came up with 33 attributes with a threshold 60%. But still, this amount of attributes is large, and we needed to focus just on the most important attributes that will highlight and resolve our lithofacies. Another point that if we just use the attribute resulted from PCA, some of these attributes themselves are highly correlated with each other and has like a linear relationship. So we needed another part or another matrices to, like Alvaro mentioned earlier, we needed like mutual information, and we also used another matrices to focus on specific attributes and proceed with them to generate the sum volume. Here we implement three different matrices: Pearson and Spearman and mutual information. Each one of them can help us to focus and reduce the redundancy between the attributes. Why is that very important in this process? Because it prevents the overfitting, also give us highly interpretable results, also enhances the computational efficiency. Because if you proceed with 33 attribute, it will take you more time and more resources comparable if you go with 22 seismic attributes. Here is some of the examples of the seismic attributes selected: sweetness attributes and instantaneous and texture and spectral magnitude. After that, talking about workflow part two, we needed to generate the lithofacies log from the well logs using the k-mean clustering. Here is the kernel density plots, which help us to show and compare between the different well logs. And finally, using them, we will choose the 6 well logs that we'll use in the lithofacies log generation. After that, we will generate our sum volume. Here's the different process. When we start the workflow to generate the sum volume, some people like or some practice go through different grid size. But here for this project or this area of interest, we will use sum from 6 by 6 through 11 by 11. Why is that? Because when we try to go smaller than 6 by 6 or larger than 11 by 11, the global fit decreased, also the miss classification increased. So that's why we just focused on into a 3 or 4 just for grid size. After that, when we do our analysis in Paradise, we have two values that help us to evaluate our models: Kramer value and the global fit. From these two values, we came up that sum volume 11 by 11 is the best one and gives the highest global fit, also gives the best Kramer value. It's reached 7 or 0.73 percentage, which like 73 percentage. Also, we confirmed the results with the normalized confusion matrix, which gave us also like 72 percentage. The two techniques are different, the normalized confusion matrix and also the global fit or Kramer value, but the final values from both of them are nearly the same. After that, continue with the workflow part 2.2. Here is another example from one of the well used for the prediction process, which is CCS1. Here you can see the subtle response from the amplitude data, which will make it harder to differentiate between the different lithofacies if we just use the amplitude volume. But in this case, when we use sum 11 by 11 or the lithofacies prediction workflow, we can effectively resolve the transition zones or the Baffles or the shaly sand from the medium fine sand, which is most dominant lithofacies in the lower part in Mount Sinai. After that, we did our validation, which we call like blind well test for CCS2. Here is the normalized confusion matrix, and the overall accuracy reaches like 87 percentage, which is very good in this highly mixed lithofacies. And this table highlights the per facies prediction accuracy, which is like 86 percentage for fine sand, and for the medium fine sand, 90%, which is very good. And for sand and shale, it reached like 87 percentage. After that, we need to highlight the comparison between the predicted lithofacies and the seismic inversion. And for clarification, here we used the legacy seismic inverted porosity volume from the IBDB dataset. It's model-based inversion. And also it implemented the four wells. But for our lithofacies prediction, we just use three prediction wells and one for validation. And here you can, in the left-hand side, you can see from the lithofacies prediction, you can see the buffle and the transition zone, and also the fine sand, which considered the high flow zones, and the main reservoir, which is the medium fine sand. So to quantitatively make assessment or comparison between the seismic inversion sensitivity towards the lithofacies and the lithofacies prediction results, we used COIM heat map, which show us the correlation between the three different volumes, the amplitude volume and the porosity inverted volume, also the sum 11 by 11 against the lithofacies. Here we can see that the sum 11 by 11 give us the highest correlation with the lithofacies and the transition zone, especially the most important transition zone, which is from the fine sand to buffles or to the sand and shale, and also from the medium fine sand to sand and shale. Why this is very important? Because this transition zone represents the transition from the reservoir rock to the seal, or from the seal to the buffle, or from the reservoir rock to the buffle zones, which will give you some insight about the risk or pressure buildup, as I will show in the next slide. So, some of the key points about the Paradise lithofacial prediction or the results here, or the geological relevance, the some lithofacies prediction highlights the high permeability and the high porosity zones, which is considered the high quality units for storage, and also give you some information about the low quality or the poor quality lithofacies or zones, which you can avoid when came to the storage process. Another key points is the sum 11 by 11 highlights the reservoir to shale to the shale transition zones, also the discontinuities that indicate the leakage or the migration pathways. The final key points is the sum-based stratigraphic mapping can support the pressure buildup detection. How we can do that? Because when you have some insights and about the transition zone, for an example, from the medium fine sand, which highly permeable and have a higher porosity, to the seal or the buffles, which less impermeability and less porosity, this transition can make like pressure buildup, and this is very important when it came to monitoring activity or the leakage effect. So to summarize the key advantage or the key points from Paradise Lithofacies prediction workflow, the first one is considered a data-driven workflow, which relies just on two input parameters, the seismic attributes and the well logs. So no need for wavelet extraction or low frequency modeling or the another practices when it comes to seismic inversion or traditional workflows. The second key point is the efficient error handling. This is something I really like about Paradise because uh, every part is separated from the another when it comes to the errors. You can retrain or redoing a specific part without the affecting of the another parts. For an example, like you can face some issues like attribute redundancy or neuron misclassification, but this can be addressed so quickly. So you can retrain the sum grid without retraining the entire workflow. The third point is that error don't propagate. This is like when you have some issues in, as I mentioned, when you have some issues in specific part, you don't need to rerun the entire workflow. The final point is the QC. QC is automated here in Paradise in this workflow because when you do your lithophase prediction, automatically when you get the result, you will get the global fitting values and the Kramer values, which you can proceed with them and make your validation and evaluation for the accuracy. So this data-driven workflow and modularity represents a huge advantage in terms of automation and error handling and the time to value, making it more robust to human errors and also less dependent on the parameter or the make it less dependency in terms of number of parameters you use in this practice or in the prediction process. So talking about some CCS application, and I want to highlight that in this table, you can see the three main parts will affect the storage process. The first one, uh, the main reservoir body in orange, which is the lateral sand body extended from the north to the south. Also, the high flow units or the high flow zones, which represent the fine sand. These high flow zones play a very important role when it comes to the carbon dioxide movement or migration pathway because it accelerates the process. It accelerates the process of CO2 migration because these high flow units have a high permeability and higher porosity. So when we try to analyze the 4D seismic monitoring surveys against our results, we find a very good match between the high-risk zone, which represent the overlapping between the four plume CO2 layers. Also, uh, this high-risk zone represents the area has a higher concentration of fine sand, which is the high flow zones, and also less concentration of the medium fine sand. That's why we consider it a higher risk zone. So this fine sand play a crucial role. It has like a higher porosity, as I mentioned, and a higher permeability. This higher permeability units acts as a injectivity enhancers, so help the CO2 and accelerate from its movement and give us some information about the migration pathways. So that's why we need this advanced workflow, which give us a higher detectability and a higher resolution in terms of resolving this highly mixed lithofacies. The first point is give us a 3D lithofacies detection overview, which help to give us higher resolution in terms of the detectability. The second point is support the optimal injection well placement. So when you need to inject more carbon dioxide, you will avoid the poor quality lithofacies. The third point, it will reduce the risk of leakage and pressure buildup. Why I'm saying that? Because right now you put your eyes in the area which consider high risk zones, and you can avoid them or you can focus on them in terms of monitoring activity. The last point is integrating this lithofacies prediction workflow with the fall detection will give us a more better insights about the subsurface system and from stratigraphic point of view and also from structural point of view. Here's like another example between the predicted lithofacies cross-section, which highlights the migration pathway for the carbon dioxide. Also, another cross-section highlights the predicted lithofacies and the identified carbon dioxide plumes from the 4D monitoring surveys. And again, we find a good match between both areas, the high-risk zone from the lithofacies prediction and from the identified plume layers from the 4D surveys. So, as I mentioned before, the favorable migration pathway for carbon dioxide will be highlighted by the high flow units, which consider the fine sand. That's why we can focus on this specific migration pathways in terms of monitoring or in terms of getting more structural interpretation into them. Finally, I want to provide my acknowledgement for all of the contributors in this work and all the data provider, Geophysical Insight and Texas A&M University. And I want to thank you again for your attendance. Thank you.
All right, we've got a few minutes for questions before Robin's talk. Some good questions here. Dr. Kurt Marfit, welcome, Dr. Marfit. He asked if you could please clarify what you mean by neuron misclassification.
Yes, neuron misclassification. It's like when you have like mispredicted or misclassification, when you make your accuracy assessment, you will find that the percentage of agreement between the predicted lithofacies and the true lithofacies is less than expected. So that's what we mean about misclassification. When you have a higher grid size, for an example, 12 by 12 or more than 12 by 12, you will have misclassification in terms of, yeah, you will have more number of neurons, but these neurons will overlap with each other. That's why they will like make the prediction process have a less accuracy.
Okay. And I think that's to be expected. You're saying there's an optimum in terms
Yeah,
of the SOM topology, and you use the statistics as well as visual corroboration to the wells to guide that
yes.
selection of the optimum SOM. Ahmed asked, on slide 10, there seems to be rock flow units 2 and 3 are correlating perfectly. Is there any explanation for this, especially they are from your well penetration? Slide 10.
Yeah, this one. So he talked about the high flow units, the yellow one, which represents the fine sand. Uh, if you can highlight the question again, please, Hal.
Yeah, the question is, it seems your rock flow units 2 and 3 are correlating perfectly. Is there an explanation for this, especially that they are far from your well position?
Yes, because this is the natural distribution of the high flow units. Like we just wanted to highlight the direction of the carbon dioxide migration from both injection wells, and it will be towards the high flow units or the high concentration of flow units, which will transit the carbon dioxide from the injection well towards the high concentration of these units, towards the north and towards the far south.
Okay, and Ismail asked, how did your attribute redundancy affect the results in this case?
All right. Talking about attribute redundancy, as I mentioned, if you just depend on the PCA, you will have some of the attributes which have linear relationship between each other, which highly correlated with each other. So you may get overfitting or some overlapping between attributes, which is not necessary. And also in terms of the computational resources, you will reduce the computational cost and resources if you redoing the mutual information or the Spearman and Pearson correlation matrices. It will help you to just focus on the attributes that's most related and most important in terms of differentiation, the different data sample and Lithofacies.
Okay, and we've got time for one more question. Jose asked, he did not see a simple well seismic tie in any of the presentations.
Yeah, yeah,
Are,
yeah.
are we underestimating
This
this crucial step to be sure we are in the right events, or is it simply assumed?
not simply assume because most of the legacy dataset are in the depth domain, so there is no need to do the well to seismic type.
But
Can I address this
yeah,
question,
please go
Hal?
ahead, Alvaro.
Yeah, yeah, that's very important point. In this case, the lithofacies and the sum have to tie many times to within one sample. So tying seismic to synthetic, we consider it like a two-step process. First, the
Mhm.
regular seismic to synthetic tie, and then that taken, we go and try to correlate the sum to the lithofacies. And many times we have to shift one or two samples to have the right
Mhm.
lithofacies going into the right neuron of the self-organized maps. So to answer your question, it is a very important step. Here we are not showing the seismic to synthetic tie. We take it that it's well done, and then we try to concentrate on tying lithofacies to some neurons.